Okay, there's a couple of you here. We'll get started in a couple of minutes. We're going to talk about the basics of GRE and Gmat probability. To start out, since there's a couple of you here, either tell me in the chat or or just verbally. Are you guys here for the GRE or the Gmat? Taking a look at both. Okay, one here for Gmat. Hey Taylor, welcome to MyGuru's online classroom. A couple of Gmat folks here. Okay, since there are three of you here, we'll get started. So yeah, welcome to MyGuru's online classroom. Today we're going to be talking about the basics of GRE and Gmat probability. We're going to look at a few general strategies to master probability questions. Here's what we're going to do. We're really going to kind of talk about probability probability on its own, as well as probability in the context of some of the more, some of the trickier questions like combinations, combinatorics, counting, things like that. All right, so here's the thing. We're going to, first of all, look at some general high-level strategies. So I'm really going to kind of tailor this both to the GRE and the Gmat, but a little bit more to the Gmat, I think, since since a couple of you are focused on that one. So here's the thing about probability. All right. Let's get this set up. First of all, can everybody see the screen okay? The whiteboard? Okay, so probability on Gmat. Here's a reason why probability tends to intimidate people. Probability and combinations, combinatorics, they tend to be the kinds of questions that show up in the difficult sections of the test. All right. And because probability and combinations are a fairly, there's a lot of logic involved. So even if you know kind of the the basic rules, it can be a little bit tricky to figure out what exactly is being asked. So what I want to do first of all is kind of like go over first of all kind of general test strategies for handling probability. And then kind of get into some of the some of the fundamentals, what you're going to be looking for, and then how you're going to tackle those actually in the context of of real test questions. So the first thing to keep in mind is how you tackle probability questions is really going to depend in part on how you're doing on the test. All right. So on the Gmat, this thing is out of 800, right? So if you are at say a 500 to 550 level, you're less likely to see them. All right. These tend to be, and there are exceptions, tend to be let's say 650 plus level questions. Meaning that because you're all now familiar at this point with kind of the computer adaptability, computer adaptiveness of the Gmat and the GRE. It's done a little bit differently in each test, but the better you are doing, the more likely you are to see one of these questions. It could be that you'll see like a kind of a fundamental level question in in one of the median level questions, but they can be quite tough. All right, so one thing to keep in mind is don't be afraid of them. All right, probability, these types of questions show up in it's probably going to be like 10% of the test or less. All right, and that doesn't mean that 10% of the test is going to be probability questions. It means 10% of the test is going to be some of these miscellaneous, difficult type of questions in which you might see probability show up. So 10% of both the GRE and the Gmat is going to be, what they call, considered to be tougher stuff like probability, combinations. This can also show up in the context of, work grade problems, maybe harder coordinate geometry. Counting methods, things like that. All right. So the thing is, depending on how you're doing, if you find that you are getting around, say, 550 or 600, you really want to focus your attention where it matters. Things like kind of arithmetic, number properties, and algebra. When you start to do better, and you're kind of getting into the, where you really want to rack those final points up to get well into the 700s, that's where you're going to want to really kind of pay attention to some of these sort of fringe problems like probability, combinatorics, stuff like that. So that said, let's take a look at, kind of what probability actually entails. All right. When we talk about probability, and I'll ask you guys, what's the definition? What do we actually mean by it? You can go and type it in the chat room if you like. Chat with them. Yeah, exactly. Right. So it's outcomes that you want over total outcomes. Desired outcomes over total outcomes. So those generally pretty straightforward. Now, towards kind of, in terms of the basic rules, you want to be aware of when you're going to use, what you might think of as your kind of and probabilities and or probabilities, right? Okay, so for example, let's take our standard six-sided die or something like that, right? You're going to start with the basics just to make sure all the fundamentals are down. So if you've got a six-sided die, right? The probability of throwing a 3, for example, that's obvious, right? That's going to be 1 out of 6. All right. Okay. Then you want to figure out if we're dealing with, kind of successive independent events, for example. So what's the probability of saying, of throwing a 2 and then a 3? Of a 2 and then 3. Well, that's going to be an and probability, right? Because we got to prove the probability of 2, which is going to be 1 out of 6. Times probability of 3, which is also going to be 1 out of 6, right? That's going to be 1 out of 36. Okay. That is distinct then from what you might think of as your or probability, right? Which is what's the probability of getting a 2 or a 3, for example, all right? Then you're going to add. All right, so simple rules. Now, I mean, I'm starting at the basics, so this stuff may be, completely straightforward to all of you. We're gonna move up to more advanced stuff in a minute. So and is multiply, or is add. All right, straightforward. Okay, now you want to be familiar with the concept, and I'm probably not going to use this in the test itself, but you want to be aware of something called mutual exclusivity, right? All right, are events dependent? Are they independent? Are they mutually exclusive? So dependent, mutually exclusive. All right, so basically how is one event depending on another event? So for example, if you've got that six-sided die, all right, you can only get a 1, 2, 3, 4, 5, or 6, all right? So and the probability of everything is going to have to add up to 1. All right, so if I add up the probability of every single event on that die, probability of 1 plus probability of 2 plus probability of 3 plus, P of 4, 5, and 6, it's going to be 1, 6 plus 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 1, 6. It's all going to add up to 1, right? Okay, so that stuff is pretty straightforward. Say you have something that's a little bit trickier. Say you have something like the probability of, let's do it over here. Probability of 2 independent events, where one has nothing to do with another. So let's say, for example, the probability of rain on Monday equals 30%. Probability of rain on Tuesday equals 30%. Oh, can everybody hear me? Or can everyone else hear me? All right. Okay. If there are audio problems, we're going to have we're going to record this anyway, so you will have access to this. But yeah, so it looks like it's not on the end here. So yeah, so hopefully things will click into place in a minute or two. and I'll try to, in the case there are audio problems, I'm going to write as much as I can on the board, just so we have kind of, everything that's, that's down. Okay, what if you've got something like this? This is a little bit different, all right? Because we don't have a situation where you've got things that are mutually exclusive, right? So with the dice situation, we had mutually exclusive events. You could not have a 2 and a 3 at the same time, right? You could not have a 4 and a 5 at the same time. It was one or the other. So the probability of all of the events had to add up to 1. This is a little bit different, all right? If you've got probability of rain on Monday and probability of rain on Tuesday, if I asked you, what's the probability of rain on either day? Any thoughts on this? Now remember, normally I said the OR probabilities would be add, right? So for example, if we were dealing with a die again, if I said, what's the probability of getting a 2 or a 3, it would be 1/6 plus 1/6. Is this the same situation? Any thoughts? Let's be a little bit graphical about it, right? So let's say, okay, let's actually draw a little chart, because it's always a good idea to draw as much as possible, be visual, right? All right. So you've got Monday, you've got Tuesday. The probability of rain on that first day is 30%. Probability of rain on that second day is 30%. What's the probability of rain on either day? Now it's easy to treat this exactly as if it's like, oh well, it's going to be exactly like the dice, right? The problem is that these are not dependent event. These are not independent. I'm sorry, these are independent events. What happens on Monday has got nothing to do with what happens on Tuesday. So if we're looking at the probability of it raining on Monday, if it's raining on Monday and Tuesday, we don't want to double count that. All right. So let's take a look. Let's say, for example, what if the probability of raining on each day was 60%? Well, then it'd be like, well, wait a minute. Okay, then it's 60% plus 60%, which is 120%, meaning that it's more than the 100% chances of it raining on either day. That's impossible. What's wrong? Any thoughts on why it's not just 30 plus 30 in this case, like it would be on the in the dice situation? Well, the thing is, here you've got overlap, all right? Because the thing is, you don't want to count. If you want to figure out if it's raining on Monday, we don't care if it's raining on Monday and it's raining on Monday and Tuesday, right? So what we want to do, we want to subtract the and probability. So what you would have here, this is similar to Venn diagram questions and things like that. So what you really have here is on Monday, you've got a 30% chance of rain. Okay. And then we've got our or. So we want to know, well, what's probably going to rain on Monday or Tuesday? Okay. So then you'll add, okay, plus 30. But now you got to subtract. Well, it should be really 0.3, right? Because we're talking about 30%. Now you have to subtract the probability of Monday and Tuesday, because these events have nothing to do with each other. You don't want to double count it. All right. So it's going to be probability, or I'm going to use the sort of like the traditional notation here. Probability of rain on Monday plus probability of rain on Tuesday minus the probability of both. And that's your and probability that you have to subtract. All right. Minus your probability of rain on Monday and Tuesday. That's got to be subtracted. All right. So it's really going to be 0.3 plus 0.3 minus 0.3 times 0.3, or 0.3 squared. All right. So you'll end up with 0.6 minus what, 0.09. That's going to equal 0.51. All right. So it's a little bit of a trick. So you want to be aware of whether you're dealing with independent or dependent events. The next probability, well, look at it this way. You can think of it in terms of a Venn diagram. All right. Say the probability of rain here is 30%, right? The probability of rain here is 30%, right? You don't want to double count this, right? Because if we want to know, well, is it going to rain on Monday or Tuesday? Here's your Monday, there's your Tuesday. You want to subtract that because you've already counted it with the 30% plus the 30%. So that's kind of, every now and then you'll see the question where probability in a Venn diagram can kind of can overlap. So this is a little bit different than the dice situation, because if you're talking about the dice situation, right? So draw one of these out. This is a rule for independent events where one's got nothing to do with the other. So if you look at the dice situation, right? Everything. Probability, these are all mutually exclusive, right? These things are all going to add up to 1. But the events here in the rain situation are not mutually exclusive. All right. So here with a die, because there's only 6 possibilities, right? There's there's a 1, there's a 2, there's a 3, there's a 4, there's a 5, and there's a 6. You can't have one and the other, right? So it's like each one of these. Sorry, that's a bad drawing. Each one of those is going to add up to each one of those probabilities is going to be 1/6, and the total is going to be 1. All right. Let's go to another type of probability. This is where we're talking about replacement and not replacement. Have you guys come across this sort of thing? Events. Yes, exactly. Independent but not mutually. Yes, independent but not mutually exclusive is the range situation. You got it. Okay. Events involving replacement or not? You've probably seen this. Yes, exactly. That's exactly what we're talking about. Marbles, cards. Yeah. So let's use the marbles idea. All right. So you've got something like, here's a jar. Got some marbles in the jar. Not a very good jar, but here's what it is. Let's say there's. I'm not going to draw the marbles. Let's say there's 5 purple. Actually color code these. So there's 4 red. All right, and then say there are. Oops. Let's keep those. Let's go with green. 2 green. All right. And I ask you, what's the probability of just reaching in there and picking 2 reds? Okay, hold on one second. I got an audio problem. One second here. All right. Okay, so 4 out of 11, 3 out of 10 without replacement. So what's going on here? So the basic situation then is that, yes, we are, okay, the thing is we need to make sure that we're picking a red to begin with, right? So the first probability is going to be 4 out of 11, right? 4 out of our total marbles. Okay, that's fine. But the thing is, in order to, choose the second marble, yeah, sorry. In order to choose the second marble, we already have to chosen that first red marble, right? So now that's gone. All right. So now we kind of satisfied the first condition. It's like, well, okay, we need to grab the first marble, which means now there's only going to be 3 red marbles left, right? And then 10 total. They simply multiply those out. All right. That is different from the with replacement. If I said, for example, what's the probability of choosing a purple marble, putting it back, and then choosing a green marble? Well, then it would simply be, well, okay, fine. Then the probability of choosing the first marble would be 5 out of 11. I put it back now, right? So there's no, so I've replaced it. And then choosing a green is going to be times 2 out of 11. All right. So be aware of the the replacement situation. Okay, next is sometimes you will come across probability questions that deal with the terminology at least. So say this again. Okay, yeah. Sorry, so one green and one purple. I'm not quite understanding the question there. It's probably a little miscommunication. Okay, what? Okay, yeah, okay, yes, I see what you're talking about. Yes, you were completely correct. Right, so that's the OR probability. So it's like, right, so we'll have the green then purple. May not be the same as the purple then the green. So you need to like make sure that you're accounting for both of the probabilities. Yeah, I see what you're saying. Okay, now let's talk about at least probability. Let's say I asked you, for example, what's the probability of, let's see. Okay, let's do it this way. You flip a coin 4 times. All right. What is the probability of tossing at least one head? Okay, 15 out of 16. All right, so the thing about the at least probabilities is you're really talking about at least one is really the same, right, as 1, 2, 3, or 4, right? So because of those laws of mutual exclusivity, right, because the probabilities are going to sum up to 1, you could really say it's going to be 1 minus the probability of getting 0 heads at all, right? And Deepak here is way ahead of things, so that's exactly right. So just kind of like lay out how kind of how to get there. So 1 minus the probability of 0 heads. 0 heads is really the same as saying all tails, right? And the probability of all tails is going to be 1/2 times 1/2 times 1/2 times 1/2, right? And that's going to be 1 out of 16. All right. Okay, hold on one second. I want to take a look at some of the questions I've got here. We're going to get into combinations and stuff like that in a second. I want to do, let's go and take a look at a efficiency question that you might see on an Gmat. I want to move this question in. This way. Okay, so what I want to do is kind of lay out the general probability rules, and now actually get into an actual kind of test environment. And then what we're going to do, we're going to move on from the kind of the core pure probability stuff, over to the combinations, permutations, and things like that, because probability and combinations are often inextricably linked. Okay, data sufficiency. Now you've all seen these. If any of you are taking the GRE, this is not going to this kind of question won't apply to you. What they're really looking for, also kind of write down. I know you all know this, but the idea is you want to figure out if you've got enough information from each one of the. Oh, wait a minute. I'm missing a statement here, aren't I? Hold on one second. I'm going to stop sharing the screen. I didn't copy this properly. I'll grab this 1 second. Half a second here. That's why, I only copied statement 1 and not statement 2. So here it is with statement 2. Okay, here we go. Sorry about that. Let's go back here. This should do it. I'll make it larger so everybody can see. Okay. Now keep in mind again for the GMAT, let's put down the answer choices. So remember, choice A is statement 1 alone is sufficient. B is statement 2 alone is sufficient. C, you need both. D, either is sufficient. And E, neither statement is sufficient. Now I know if you guys are have been doing GMAT studying, you're fine with this. All right. Okay, so let's take a look at this. 9 independent trials. What is the probability that outcome A happens at least once? And I'd say the wording in statement 2 is probably a little bit ambiguous. So what they mean by a single trial, this should really say in any individual trial. That would be a little bit better wording. So I'm going to say it like this. Say the probability of outcome A resulting in any individual trial is 1/3. Just a little bit clearer. Okay, so 9 independent trials. What's the probability that outcome A happens at least once? Hold on a second. Okay, let's look at each statement independently. All right, so statement number 1. The probability that outcome A does not happen even once in any of the 9 trials is 0.026. Is that going to be enough? Is that sufficient to tell us the probability of outcome A happening at least once? Excuse me. It is. Deepak is correct. You want to say why? It's really analogous to that last question. Yeah, exactly, right? So it's really, exactly. So it's really analogous to the, to the last question that that we did with the coins, right? Yeah, exactly. It's basically 1 minus probability of this not happening at all. So that's going to be enough. Okay, statement number 2: the probability of outcome A resulting in any individual trial is 1/3. All right, statement 2 going to be enough. So there, it's just like the coins, right? Because if we know the probability of outcome A, happening, we know the outcome of A not happening, right? So it's like, if we know the probability of something occurring is 1/3, we can figure out the at least probabilities, right? Because it's simply going to be 1 minus the probability of A not occurring. So it's exactly like the coin situation, meaning that either situation is going to be sufficient, right? So that's sufficient. That's also sufficient. All right. Let's do one more probability type question. This is, I think, from a GRE one. This is a little bit different. 1 second. This one's going to be a bit more straightforward. Okay. Okay, this is probably more of a let's say this. Actually, no, this is not a GRE question. This is a Gmat question. Another data sufficiency. Take a look at this one here. Now, this isn't really about the probability calculation. This is really more about kind of the definition of probability. Is like, can you determine kind of logically how much information we're actually dealing with? Why don't you guys take a look at this question for a little bit? And once we do this one, we will spend a little bit of time with the combinations and permutations. Okay, any thoughts on this? All right, let's take a look at statement 1 first. Now, remember, for these kinds of things, you want to kind of simplify as much as possible. You've got, got $1 loose change. Here they're kind of, they add additional words to, to explain the currency, but, kind of filter out the stuff that you don't need. All right. We're saying we've got one random coin. What's the probability of a nickel? Let's say probability of a nickel. Okay. Statement 1, there's exactly 7 pennies in this pocket. Well, okay. So what does that 7 pennies in this pocket say? Well, what that's saying is that everything outside of the 7 pennies is going to total $1.30, right? Or $1.30 or 130 cents. All right. Now that is clearly not going to be enough to tell us, how many nickels there's going to be, right? There could be 13 dimes, right? There could be, 26 nickels. There's lots of ways of doing it. We don't have enough information to figure out how that remaining 130 is split up. All right. Then looking at, all right, so that's going to be insufficient. Statement 2, there's exactly 3/4 in this pocket. Well, okay, so that accounts for 75 cents, which is great, right? But that means there's going to be a remaining 62 cents, right? I'm doing my math right. Yeah, 75, because there's going to be 62 cents left over. All right. So what it's really saying is, can we determine how many nickels are going to be in, in 62 cents? No. Right. Again, it could be, any combination of nickels and dimes and 2 pennies. So this one here is going to be insufficient. Now, looking at both of these together, it's like, well, okay, if there are 3/4 and 7 pennies, well, again, that is also going to account for, that's going to account for our 75 cents plus 7 pennies. That's 82 cents. We still are not going to be able to determine, how many nickels there are. So we wouldn't be able to figure out the probability. All right. Now that's really less about probability, more about kind of wording. But the thing is, you need to know when you're looking at a probability question when you actually are going to need to apply the probability rules, and when you're going to kind of need to look at something a little bit more logical. All right, let's move on to a related topic, and this is the one that kind of trips everybody up: combinations and permutations. This is kind of collectively called combinatorics. All right, so 1 second. More colloquially known as counting methods. So here's the thing, all right? Let's start out from the very beginning, fundamental counting principles. So if you've got something kind of really straightforward, if you've got something like, say I have, I don't know, let's say I've got 4 kinds of coffee, right? I've got, say, I don't know, 4 breakfast meats or something. And I've got, let's say, 4, I don't know, let's say 4 types of breakfast potatoes, right? Actually, no, not 4. Let's do 4, 3, and 2. I don't know where I'm coming up with this. This is pretty random. All right. 4 kinds of coffee, 3 breakfast meats, so there's, 4 kinds of coffee. There's, whatever, there's decaf, there's some kind of dark Colombian coffee. There's, whatever. There's, with the breakfast meats, maybe there's a, I don't know, there's a, whatever, there's a ham and a steak or something. And 2 breakfast potatoes. How many different breakfasts could I make? All right. This is going to be pretty straightforward. All right. It's simply going to be 4 times 3 times 2, because everything can be grouped with everything else. All right. So you have a total of 24 different types, 24 different, you think those arrangements. All right. And you can think of it kind of graphically too, right? So, I mean, you could kind of draw this out and say, well, okay, let's say I've got, okay, my coffees, here's my coffee. There's 1, 2, 3, and 4, right? Okay, there's 4 of those. Any of those could be potentially paired up with any, any kind of, any of, 3, right? You can imagine those tree diagrams. Now, granted, you're not going to do a tree diagram for, for complicated stuff, but any of those can be paired with any of these 2 potatoes, right? So you can imagine counting them all up, and you'll get, 24 of these things. Okay, that's kind of like the first step. Okay, next step is to kind of apply that to our arrangement type of questions. Say, here's the example I always give. Well, say you have something like this. Say you've got a horse race. All right. And there are 8 horses in a race. And I'm not going to apply any restrictions here. Okay. And I want to say, okay, fine, there's 8 horses in a race. How many ways can those horses finish? And we'll do it both visually and mathematically. Anyone know? You got 8 horses. I'm not putting any restrictions. In how many ways can those horses finish? How many arrangements? Okay, well, let's visualize it first. All right, so essentially what you've got, let's draw it out. It's like 1, 2, 3, 4, 5. 6, 7, 8. All right. So what's happening is we don't know. Any one of those 8 horses can populate kind of that first winning slot. But once we've locked that down, you've only got 7 left. Once you've locked that down, it's 6, right? So you all know this is where kind of the factorial stuff comes from. And this is really kind of, related to that fundamental theory, counting series, right? You've got 8 possibilities for the first, 7 possibilities for the second, 6, and so on down. So it's going to be 8 factorial. If we're thinking about the formulas, that's going to be up with the formula on the left. It's going to be n factorial, where n represents your total starting number. N equals number, whatever. Number of events, you could say. Let's say number of horses. All right. Let's say number of items. Okay. Now let's restrict things. Now, this is basically kind of unrestricted arrangements, unrestricted permutations. Okay. Now you're probably not going to see the terminology permutation on the test, but but some of you have learned it that way, so just so that you know. But they mean arrangements. You will also see this the terminology order matters, which means that if horse number 8 is in the first slot, that is not the same situation as horse number 8 in the 5th slot. The order makes a difference. We need to count all of the orders. The next situation is, say you had something like this. Say we wanted to do, okay, how many ways can the top 3 horses finish? That's a little bit different. Now we have a restriction, all right? And how many ways can we have 3, 3 finishing, how many top 3 finishing arrangements can we have? This is going to be a little bit different. So you're starting out the same way. We still have the same, 8-horse race, all right? We still care about that first one. We still care about the second one. We still care about the third one. We don't care about anything else. All right? We don't care about all the permutations of the stuff at the bottom. They don't matter. They're redundant. But there's lots of ways, that those kind of bottom 5 horses could have finished that we don't care about. So it's going to be 8 factorial. All right? And then it's going to be 8 minus the subgroup size. All right? So what that really turns into is, 8 factorial over 5 factorial. And so that 5 factorial in the bottom here, that's going to cancel out everything from those 5s on down up top. So you're going to be left with 8 times 7 times 6. All right. So what's happening is we're ignoring everything down here. We're dividing it through. It's redundant. So it's just going to be 8 times 7 times 6. So the formula for what's really kind of here, it's really for arrangements of a subgroup. Formula for that is going to be just what I've got over there, your n factorial over n minus that group size. That's the second step. These are arrangements again. The order still matters because 8, 7, 6 is still not the same as 6, 7, 8. All right. The next situation is going to be what's known as combinations. If I said something like this, now let's say this were a trial heat. All right, this is a trial race, and I want to choose the best 3 horses to go on to to a championship. I don't care how those top 3 horses have been arranged. I just want the 3 best. All right. So I say something like this. In how many ways? Well, I'll say it like this. How many groups of 3 horses can be selected to advance to the championship? This is a little bit different, all right? Because here we're talking about what's known as combinations. All right, so instead of arrangements, because we don't care about the arrangements anymore, we're just talking about the group size themselves. Groups, combinations. All right, so here we do not care about the arrangements. So order does not matter. All right. So here, what's going on, you start things the same way. All right, you still have your, well, okay, fine. We've got 2, 3, 4, 5, 6, 7, 8. We start the same way as we did the last one, right? It's like, well, okay, how many top finishers do we have? We got, 8 at the top, 7, 6. But the thing is now, we don't want to count all of these. We don't want to count, say, 8, 7, 6, 8, 6, 7, 7, 6, 8, 7, 8, 6, 6, 7, 8, and 6, 8, 7. Because these are all redundant. We want to count this entire thing as a single group. So what you're going to do, sorry about that writing, cleaner. It's a single group. We want to divide by the redundancy. So what's going to happen here is going to be 8 factorial. Everything else starts the same. 8 factorial over your 8 minus 3 factorial. But then we're going to divide by all the ways that we could have permuted, that we could have arranged that group size that we don't want to count. 3 factorial. All right. Order does not matter. So the formula here is going to be n factorial over n minus r factorial times r factorial. Okay. Okay, so let's see, hold on one second. Okay, there's a couple of other things to keep in mind. Whenever you see something that kind of suggests redundancy, you might take that approach. So, for example, let's say we have something like this. Okay. How many 4-letter words? Now, by 4-letter words, they don't have to mean anything. All right. I just mean any 4-letter fake words, whatever. So it's like let's say ABRA is going to be a word for our purposes, okay? Or DRA, well, DRAB is a word, but they don't have to be actual words. All right. So how many 4-letter words could be made from abracadabra? I probably should have given you some answer choices, but that's all right. This is basically similar. This is going to combine both groups and arrangements. All right. How would we start? Well, first of all, you want to figure out, well, how many letters are you actually dealing with? Well, you're dealing with 11, right? And what do we actually want to figure out? Well, okay, it's really going to set it up the same way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. We only care about those top 4. We don't care about anything down here. So it's going to kind of start out the same way, right? So it's going to start out with the kind of our permutation approach. You can imagine, say, well, that's going to be, well, fine, it's going to be 11 times 10 times 9 times 8. And the thing is, the order makes a difference here, right? Because if I look at, say, let's look at kind of that first grouping, that ABRA. That is not the same as, BRAA, right? It's a different word. It's also not the same as like, RAAB, right? So I'm actually concerned with arrangements here. So what I'm really starting out with is I'm really starting out the same way. I'm really starting out with my 11 factorial over my 11 minus 4 factorial. So I'm really starting out with my permutations, right? My arrangements. But I'm not done. Anyone know what needs to be done at this point? Well, this is really kind of like bringing in, excuse me, the I think we'll finish this one. I think we'll do one question, then we'll wrap things up. So error messages on my. Okay, so what's going on here is we've got some redundancies, right? Because the thing is, even though ABRA can be arranged in lots of different ways, we don't want to double count all the ways in which, like, you know, the A's can be arranged, right? We've got duplicate letters. So what you want to do is you want to divide by the duplicates. And you want to divide by all permutations of the duplicates, right? That will get rid of the redundancies of any repeated letters. So how many repeated A's do I have? I've got 5 repeated A's. So all the ways that I could, you know, take that group of A's and arrange them, I don't want to count them. I want to divide them, you know, divide through. All the ways that I can, like, you know, potentially kind of arrange those 2 B's, I don't want them. I want to divide through, right? What else is repeated? The R's are repeated as well. So everything that's repeated is going to be divided through in the denominator. So you can think of it like redundancies are divided out in the denominator. All right. Okay, other situations that you might want to consider, sometimes you might get something where, okay, let's take something like this. Well, let's see here. Let's take a look at a tough question, which relates to all this stuff. 1 second. This kind of a difficult problem-solving question. Okay. Large, so let's see. This one's not easy. Most people I've worked on this where they're not gotten it right. Okay. How many ways can a group of 9 people be divided into 3 groups, with each group containing 3 people? Give you guys a few seconds to think about it. Okay, so let's do this. Let's actually, again, it's a good idea to kind of visualize things. All right, so we got a group of 9 people, and you know, keep in mind, whenever, give yourself a lot of time. You know, whenever you see these kinds of questions, the probability and the combinations, again, they're often linked, because you might often have to figure out how many ways can you, like, you know, arrange the group outcomes. You know, how many ways can you arrange the total outcomes, things like that. All right. So because there's a lot of logic involved in terms of kind of figuring out what's being asked, you will often want to, you know, slow down on these questions to make sure that you're really clear on what they are actually asking. So what have we got here? We've got 9 people in 3 groups. Let's set it up like this. Group 1, group 2, group 3. Here's our 9 people. Okay, each group contains 3 people. So how are we going to figure this out? Well, okay, the first group is going to contain any one of those 9 people. Sorry, the first spot in the first group. You know, they've got any one of those 8 people and one of those 7 people, right? But the thing is, because we're talking about groups and not arrangements, this is going to be a combination. It's going to be a group problem, right? So for that first group, it's going to be, if you guys remember this notation, 9C3, but that's basically going to be how many groups of 3 can we choose from 9, right? So it's going to be our 9 factorial over 9 minus 3 factorial. Then remember, divide again by 3 factorial, because we don't care how the people in that group are arranged. Once we have that group locked down, then we've only got 6 people remaining for the other 2 groups. So now we've got 6, 5, and 4. So now it's going to be 6 choose 3, right? In other words, 6 factorial over 6 minus 3 factorial. 3 factorial. Right? And then here, it's going to be 3, 2, 1. But because we've only got a remaining 3 people in a group, and it's a group of 3, we don't care how they're arranged, it's only one person. It's only one group, right? So technically, it's going to be 3 choose 3, right? Or 3 factorial over yeah. So that ends up being 1. With 0 factorial is 1. I forget the yeah. That's going to be 1. All right. So is that times that times that. But there's another redundancy that we need to figure out. We don't care how those groups are arranged. We don't care whether this group comes first, or this group comes second, or that group comes third. So we would actually need to divide again by the permutation of the group size. All right. So it would really be 9 choose 3 times 6 choose 3 times 3 choose 3 all over 3 factorial. All right, that's a tricky one. Another couple of things to keep in mind. Sometimes you will get types of questions where, lock down what you need to lock down. So for example, if you've got something to the effect of, if you have something like this, if you've got, say, 6 students walk into a classroom, right? Okay. Let's say Mark and Michelle are hall monitors, right? So they have to be on the ends. In how many ways can the students walk into the classroom? Okay. So there's a couple of things. So you want to figure out, where you kind of lock things down. Like, for example, if Mark and Michelle had to be together, right, then you kind of treat them as an individual unit. In this case here, Mark and Michelle can only be on the ends, right? So again, you've got your 6 students, and we want to figure out how many ways they could potentially walk in. If there were no restrictions at all, that would simply be 6 factorial, right? But the problem is we are actually locking down 2 spots. In these spots, we can only have Mark and Michelle. But we don't necessarily know what order they're going to be in. Or it could be Michelle and Mark, right? So what we need to do, because we have no restrictions on those middle 4, that's going to be 4 factorial. Right? And then we multiply that by the ways of arranging Mark and Michelle's position, which is going to be 2 factorial. Right? You could also think of it logically and say, well, fine, okay, I've got 4 factorial for the situation where Mark is first, plus 4 factorial for the situation in which Michelle is first. All right. Okay, that's going to wrap up the general session. I can take a couple of questions before we wrap up. And if there are no questions, I hope everybody enjoyed the class and have a good week. But I will stick around here for a couple of minutes just in case. Okay, it doesn't look like we have any questions. I will leave the board up for a little bit, and I will end the meeting here. Thank you all for attending. You're welcome. Okay, if anyone's left, I'm going to end the meeting, but thank you very much and enjoy your week.